Today, I'm going to tell you why I think social skills will be increasingly valuable in the age of AI. And when I say social skills, I don't mean etiquette or cocktail party conversation or networking. I mean the actual business of understanding people's talents and motivations so you can work well with them, the ability to gain people's trust and to influence their beliefs and mindsets. As my research shows, these are real, measurable skills that predict performance. Evolution has hardwired us to be highly efficient social learners. And personal relationships have to be built one at a time. So AI can't make up for its learning inefficiency with massive scale. And that is why social skills are probably going to matter more than ever in the age of superintelligent AI. Hi, everyone. Welcome to the Context Window. Today is part 2 of our discussion about the future of work and what skills and jobs will matter most in the age of superintelligent AI. In part 1, we talked about why AI being better at every job task you could possibly imagine would not necessarily lead to the end of work, despite many people's intuitions to the contrary. Everyone from Elon Musk to Bill Gates to Andrew Yang have predicted that AI progress will eventually lead to the end of work. I think all of them are wrong. I really do. And hopefully I convinced you too. But if you're just tuning in and you think, this guy's a total moron, what is he talking about? Well, maybe you're right, and maybe I'm wrong, but do me a favor, at least go back and watch the first episode before you conclude that I'm a moron. Give me a chance to convince you that my side of the argument is the right one. There's a deeper question here, by the way. Everyone's out there confidently predicting the future. Rationally, I know it's an impossible task. I'm surely going to be wrong. But at this very moment, I am completely convinced by the quality of my own arguments. And yet, I look back at things I've said in the past and I think, wow, that was a dumb take, Deming. What were you thinking? But here I go again anyway. Do morons know they're morons? Probably not. They probably think they are smart and contrarian. Anyway, speaking of being wrong, I want to read you a quote that may sound familiar. While no one has yet sorted out the jobs lost because of the overall drop in business, many a labor expert tends to put much of the blame on automation. The number of jobs lost to efficient machines is only part of the problem. What worries many job experts more is that automation may prevent the economy from creating enough new jobs. In the past, new industries hired far more people than those they put out of business, but that is not true of today's new industries. This quote is from a Time magazine article written in 1961. In 1964, President Lyndon Johnson formed a Blue Ribbon National Commission on Technology, Automation, and Economic Progress to confront the automation problem head-on. The commission ended up recommending a guaranteed minimum income for each family and 2 years of vocational education, among other things. Sound familiar? We've been here before. And the one consistent lesson I've learned from studying and writing about how technological progress changes work is not that it eliminates jobs on net, but rather that it leads to a fundamental repricing of skills. Mechanized agriculture shifted us from a world where physical power was scarce and you needed horses and mules and big families with strong, healthy kids to grow enough food, to a world where physical power was abundant. Skills like strength and stamina no longer mattered as much. Knowledge and intelligence became scarce. More educated farmers were faster adopters of new technologies like hybrid seed corn. People left the farms and moved into factories, where basic literacy and numeracy were huge assets. Now, more than a century later, intelligence has become, or will soon become, abundant. This won't end work, but it will lead to big changes in our economy. What kinds of jobs and skills will become scarce and valuable in the age of AI? Well, as we discussed last week, an important idea for thinking through the future of work is the principle of comparative advantage. One day, AI will do 99% of the knowledge work that we do now. But that remaining 1% will still be really important. Again, think about agriculture. Most farmers in the US today are rich, with a median household wealth of $1.6 million, even though automation has taken 99% of their tasks. Farming went from nearly every job to less than 1 in 50 jobs in the US today, and the people who left farming mostly did other things. If you went back in time and you told your ancestors that only 2% of their descendants were going to be farmers, 1 in 50, they would assume that we had mass unemployment. They would never predict that their great-grandchildren would be software developers or occupational therapists or management consultants or social media influencers. None of those things would sound like real jobs to them. Predicting the as-yet-to-be-conceived jobs of the future is impossible. But maybe we can guess the direction of travel. What is the human comparative advantage over machines? Meaning, what are some things that come more naturally to us than they do to our robot overlords? Last week, I argued that humans are much more efficient learners than large language models. AI needs much more data to learn a task than we do, like millions of times more. But once it learns, game over. The AI never forgets, it never gets tired, and it can reproduce its work at near infinite scale. What does this have to do with comparative advantage? Again, people learn a lot from small amounts of data. But we forget things, we break down, and we can only be in one place at a time. When I was a kid, I used to play video games, like a lot of video games. And my friends would make fun of me because I'd have to go in every room of the castle or the dungeon or the maze or whatever the setting was, just because I wanted to know what was there. They would make good guesses about where to go first, speed run the game, and finish much faster than me. But I needed to know everything. That's how the AI learns. It doesn't jump to the intuitive answer first. It exhausts all possibilities. Learning the entire maze can pay off, but only if you're going to walk through it over and over again, and if the floor plan never changes. So here is the key distinction. Some job tasks are low context. You might call them routine, meaning there is a well-established, correct way of doing it, and success is easy to verify. These are tasks where AI should have a comparative advantage. Software coding is the classic low-context task, because the code either works or it doesn't. It's easy to verify. And my code should run the same as your code. High-context tasks are not easily verified, because the right answer is usually, it depends. Performance in high-context tasks is dynamic, always evolving, and hard to predict in advance. The rules of the game are always changing, and they aren't written down anywhere. The right approach to solving a problem one day might fail spectacularly tomorrow. Human learning efficiency gives us a bigger edge, a comparative advantage, in high-context tasks, because success requires constant learning and adaptation. So, what are those tasks? Well, one type of work that is important for getting things done, valuable in almost every job, and consistently dynamic, unpredictable, and high context is social interaction. Working well in a team, figuring out what people want, how to sell it to them, building personal relationships, and establishing trust, these are extremely important for success in most jobs. We don't think about social interaction as being cognitively complex because everybody does it instinctively. Still, the compute required to successfully navigate a 5-minute unstructured conversation with another person is massive, much bigger than figuring out the optimal move in the middle of a chess game, for example, because unlike chess, the action space of a conversation is essentially infinite. You could say anything next, and so could your partner. So you've got to be quick and adaptable. Conversations are also multimodal. There's body language, tone of voice, pacing, those all encode meaning beyond the words on the page. And the reward structure of a conversation is murky. How do you know whether any particular conversation you had was a success? And by what standard? My point is that being able to navigate the human social world and work well with others is an incredibly important skill. We all know people with great social skills. They have lots of friends and business connections. They are great at selling and influencing others. Those people tend to be hugely economically successful, and they're happy. And yet, I think we have historically underrated the importance of social skills, certainly in economics we have, because they are so hard to measure and verify, and because they are so fundamental to navigating the world that we take them for granted. A few years ago, I published a paper in an economics journal called Econometrica with my colleague and my former student, Ben Weidman, and this paper was about how to measure individual contributions to team performance. Now, let's say you and I are on a team with some other people, and the team does really well. Who deserves the credit? Or if it does badly, who deserves the blame? You? Me? Somebody else? Something about the chemistry between us? The problem is that there are many people on a team, but only one outcome. That's a hard identification problem to solve, and you'd really like to solve it, because if there are certain people who are always making their teams better, we want to hire them and promote them and pay them more, because teamwork is ubiquitous in the modern economy. Michael Lewis wrote an article in the New York Times back in 2009 called The No Stats All-Star. It was about Shane Battier, a basketball player for the Houston Rockets. Battier didn't score many points or get many rebounds or assists. He didn't do much of anything that showed up in the box score or gained him all-star votes or other accolades. But whenever he was on the court, his teams always did much better than when he was on the bench. Here's a quote from the article. "Here we have a basketball mystery. A player is widely regarded inside the NBA as, at best, a replaceable cog in a machine driven by superstars. And yet, every team he has ever played on has acquired some magical ability to win." The article then goes on to talk about plus minus, which is a statistic that captures the score of the game only during the minutes that the player is on the court. Players like Battier don't show up in traditional stats, but they tend to have much higher plus minus than others. They play great defense, they box out so that others can get rebounds, they make the pass before the pass that leads to an easy shot, and so on. Now, the thing about plus minus is it's purely performance-based. You don't need to know what the contributions of players like Battier actually were to measure their impact. You just look at plus minus. A problem with plus minus, as the article notes, is that players are not randomly assigned to lineups. If you're always on the floor with LeBron James or Steph Curry or Kobe Bryant, you're going to look good on plus minus because they're good, not because you're good. And for the basketball nerds out there, I'm thinking of Mario Chalmers, Zaza Pachulia, and Derek Fisher, respectively. All those guys were at the top of the league in plus minus when they played with LeBron and Steph and Kobe, and none of them was particularly good, really. So anyway, Ben and I solved this team assignment problem in our Econometrica paper with a simple experiment. We measured people's individual skills at baseline, so we knew how good they were. And then we repeatedly randomly assigned them to different teams. We can then see whether some teams consistently do better than what you would predict based on who gets assigned to them. So if a team outperforms its prediction every time you get assigned to it, regardless of your teammates, you are what we call a team player. You'd be like Shane Battier from the Michael Lewis article, except if Battier were getting randomly assigned to NBA teams and lineups, and if you were 6'8" and had a shaved head. We found that, indeed, some people really do reliably make their teams better, and that being a team player is meaningful for performance. It actually matters about as much as IQ. And yet, people who were team players didn't have higher IQs on average. IQ and team playerness, what we'd call social skills, were both strong predictors of team performance. But they were independent and unrelated to each other. Being a team player wasn't correlated with IQ or education or gender or anything else, really. The only thing it was related to was something called the reading the mind in the eyes test, or RMET. And the RMET was originally created many years ago by the psychologist Simon Baron-Cohen, who is first cousin to Sacha Baron Cohen of Ali G and Borat fame, to study social cognition in autistic adults. You show people a series of faces, or even just eyes, and they have to correctly guess the emotion that the face is expressing. So it's essentially a test of emotion recognition. Like IQ tests or the SAT, it's a multiple choice assessment. There are right and wrong answers. People with autism who have high traditional IQs often struggle to score well on this test. Now, it was originally developed for a narrow diagnostic purpose, but like many other tests, psychologists subsequently discovered that RMET performance within the normal range predicts a lot of other things too. In our study, people who scored higher on the RMET were much more likely to increase their group's performance. They were team players. Team players are better at recognizing others' emotions. And then Ben and our student Yishan developed a modern version of the RMET called Perceiving AI-Generated Emotions, or PAGE, where you can easily manipulate the race and gender of the faces or crank the emotional intensity up or down. You can take the PAGE test on our website, skillslab.dev, if you want to see how you stack up. And if you're watching on screen, here is a sample item. I'll give you a second. The correct answer is pride. Now, I know what you're thinking. Isn't AI already pretty good at recognizing emotions and faces? The answer is yes. GPT-4 class models significantly outperformed humans on tests like RMET, and they were also pretty good at other social cognition benchmarks like understanding false beliefs, interpreting indirect requests, and recognizing irony. I suspect AI models would ace our PAGE test, especially since the faces are AI generated. It takes one to know one. So, doesn't AI have social skills already? Tests like RMET and PAGE measure emotion recognition, which is a necessary but not sufficient condition for being good in a team. If you're unaware that you're pissing someone off, you probably can't change course, and so you're probably not a team player. But Ted Bundy, notorious serial killer, was very good at reading people and probably would have aced the RMET, but I doubt he was a team player. Emotion recognition is only economically valuable if it helps you understand someone so that you can better predict their behavior. Again, though, AI models are already reasonably good at predicting behavior patterns, but only when people are rational, risk-neutral, and forward-looking. Homo economicus, if you will. A bunch of computer scientists at Princeton hooked up different models to datasets of thousands of real human choices about risk. So like, would you rather have $20 for sure, or a coin flip for $100? What about 35? And so on. They had multiple observations for the same person, and they asked whether the LLMs could predict people's choices. And the answer was yes, but only if the people behaved according to rational choice theory, which most people don't. The models were also not very good at predicting mistakes or predicting people who would be predictably irrational. For example, if I am super risk averse in the first 3 choices I make, I'm probably also going to be super risk averse for the next 2. The models didn't really learn about people or account for common human errors. And that's a critical distinction, because working well with others requires you to see them how they actually are, not how you think they should be. And that means reasoning backward from their behavior to infer their goals, their beliefs, and their preferences. Psychologists call this inverse planning. If you want to predict someone's behavior, you need to get inside their minds, to think how they think, even if their thinking is flawed. Inverse planning depends on the context in which a person is behaving, which you can't see in the data. If a coworker is behaving rudely, are they mad at you for something you did or said? Are they just having a bad day? Did they forget their morning coffee? Your judgment about them might change, depending on whether they are being rude to everyone or just to you, whether they are equally rude later in the day or tomorrow, or whether their favorite team won or lost in the World Cup. And you get the picture. Frontier AI models are very good at inverse planning, but again, only when behavior is rational and predictable. They struggle to predict irrational behavior. They also struggle on direct tests of inverse reasoning, where the model has to actually diagnose meaning and intent from behavior rather than just predicting it. And that's because an AI model's emotional intelligence, such as it is, comes from brute force pattern recognition, not from deeper social reasoning. I recently read a clever paper that makes this point very well. They designed a very simple task where a person walks around a parking lot to look for their favorite food truck for lunch. Now, they can't see the lot's entire grid from where they are, only the nearby parking spots. And while they know all the trucks that could possibly be present, let's say there are 6 of them, not all the trucks are actually present on any given day. So maybe 5 out of 6 on any given day, but it's a different 5 every time, for example. Now, you're walking in the parking lot. Suppose you stop at the first truck you see. What do we learn from that? We learn that truck was your favorite. You could have kept searching, but you didn't. You didn't need to know the other options. Now, what if you wander the whole lot and pick the last truck you see? Now I know it was your favorite among the trucks that were present, but I don't know where the missing truck ranked in your list, and so on. And with each step a person takes, you learn something new about their preferences. Do they stop? Do they keep going? So in the experiment, they stop the walker at each point on the grid, and they ask both people and AI models, given where this person has already walked, what they saw, what they passed up, and where they are now, what can you infer about their preferences? In a zero-shot task with no worked-out examples to learn from, GPT-4 and humans were equally likely to correctly predict the favorite truck. But AI was much worse than people at inferring the entire preference structure, and it was especially bad at making inferences about the missing trucks. The researchers then gave both people and AI a simple example to learn from prior to playing the game, and these one-shot examples improved human performance much more than they improved AI performance. AI was also much worse in this study than humans at something called inverse planning. Now, this is one level up in the game, so to speak. Inverse planning means acting in such a way that someone else can correctly guess your preferences. People do this kind of social signaling all the time without thinking about it. So the authors construct another similar task where there are 2 restaurants, again, set on a grid. An agent who is going to walk on the grid prefers one restaurant over the other, and their goal is to communicate that preference to another agent through their behavior, so no words allowed, making as few moves as possible. So one straightforward way to do that, which may be obvious to you, is to just walk directly toward your preferred restaurant. That's pretty simple. Now, the downside is it might be far away, and you might have to pass the less preferred restaurant along the way to get there. So your partner won't learn your preferences for a while. It works, but it's inefficient. Another strategy is to walk into and then out of the restaurant you like less if it's close to you. That sends a very clear message, but it also might take a while. It turns out that the best choice is often a subtle signal, like taking one step away from the restaurant you like less before moving toward the one you do. Then the other agent can learn your preferences quickly. You don't need to travel all the way to make your point. 60% of humans chose subtle signal strategies in this experiment compared to only 9% of the AIs, who mostly just chose the direct route. As before, providing a one-shot example of the subtle signal strategy improved human performance much more than it improved AI performance. And the lesson from that is we are good at making social inferences from incomplete information. I also recently read some really cool new work out of Microsoft Research, which uses public chat logs from human to human and human to AI conversations, and shows that LLMs are much worse than people at something called conversational grounding. Conversational grounding is the collaborative process by which conversation partners build mutual understanding toward a common purpose. If your boss says, "Hey, can you send me the report?" you might ask, "Well, did you mean the quarterly sales report or the customer survey report?" And then they can clarify which one they meant. Quarterly sales report, thanks. Grounding also helps establish areas of agreement and disagreement. For example, your boss might say, "Okay, so we're going to launch on Monday and fix the minor bugs afterward. Everyone comfortable with that?" And you could respond, "I understand the plan, but I don't agree that we should launch so soon before fixing potential security issues." So what you're doing there is you're clarifying that comfortable means I understand what I'm supposed to do, but I don't agree with it. Now, the Microsoft research paper found that LLMs were 3 times less likely to ask for clarification and 16 times less likely to make follow-up requests during conversations. They also show from the chat logs that early conversational grounding failures cause misunderstandings, frustrations, and communication breakdowns later on. Now, the point of all these studies is that social skills are more than just emotion recognition and surface-level empathy. They require inference over hidden, latent social variables. What someone wants, what they know, what they think other people will infer about them and their motives, and how their actions will reveal their motives and beliefs, and the costs and benefits of those revelations to them and to others. The other key point for thinking about human comparative advantage is that social inference is often individual specific. I can learn a lot about one person, but that doesn't always scale up very well to learning about another person. And this research shows that for now, or more precisely, as of about a year ago, since these papers use GPT-4 and it's already out of date, we still have an absolute advantage in many social tasks. And eventually that will fade. But I think comparative advantage will persist even when the models get better than us because of the sample efficient way that humans learn in social settings and relationships. Evolution has hardwired us for efficient social reasoning. 10-month-old infants already engage in inverse planning by watching animations where people jump over gates of different heights, and then they figure out that the person who chose the higher gate must have wanted what was on the other side of it more. So they're already inferring intent, 10 months old. Research on so-called thin slice reasoning, which is popularized by the Malcolm Gladwell book Blink, that research shows that people are able to make accurate clinical judgments about others based on very short observations. And this is human sample efficiency at work. The evolutionary anthropologist Joe Henrich here at Harvard argues that the reason for humans' evolutionary success as a species is that we are incredibly dependent on socially transmitted information. We have access to much more knowledge than we can possibly store in our own minds because we store it in other people. This social storage and distribution mechanism is what Henrich would call culture. Culture is a second inheritance system alongside our genes. Culture makes us smarter and more capable than we are as individuals because it places us inside networks containing information that no mind could contain alone. And societies that establish more efficient social brains are the ones that have survived and prospered. In other words, our social reasoning skills have been forged in the fire of millions of years of evolutionary pressure. And that is why we learn from others so efficiently. Culture is very high context, and understanding it has been essential to human survival. Now, I am certain that future models will be better at the games I mentioned earlier, and that in any case, they could be trained up to succeed on them. That is not the point. Machines learn differently than us. AI models apply sophisticated pattern recognition algorithms to massive amounts of data, unimaginably massive amounts of data. People learn by building game-theoretic models of each other and reasoning backward from behavior to update their beliefs using incomplete information and sparse data. It's a completely different paradigm. And that becomes important for projecting the future of work, because social reasoning is in fact way more complicated than any simple experiment can capture. Learning another person's goals and beliefs from their behavior is hard enough. But we live within social networks where the relationships between people differ and depend on context. And learning efficiency is especially important for social networks because the complexity of the network scales exponentially with its size. So to be precise, the number of one-on-one relationships scales quadratically. So there's one relationship in a two-person network, there's three in a three-person network, six in a four-person network, and so on. But if you want to learn a social hierarchy with two options, like I'm above or below, there are 2 to the n possible network structures, where n is the number of possible pairs. So that's 64 possible network structures for a group of 4 people, because 6 relationships means 2 to the 6th. With 10 people, there are 45 pairs, and 2 to the 45th power is 35 trillion possible network structures in a group of 10 people. A recent paper in Nature Communications shows how people manage this fractal complexity. We don't map it comprehensively like an LLM would. Instead, we build mental models to represent entire social networks based on the small part of it that we observe, and we update our beliefs continuously based on new information. Our causal models of social networks also allow us to successfully make out-of-sample predictions about how people we've observed in one group would behave in another group that we haven't observed yet. The experiment in the paper is a simplified version of starting a new job and trying to figure out office politics. People watch these short animations of 6 to 8 social interactions between just 5 people, which is a very small subset of the network. Despite only having a small fraction of the data they would need to map it out, they correctly infer the group's hierarchy and its friendship and mentorship networks. And they successfully predicted how people who they hadn't actually seen meet would interact, and what type of relationships those people would have: authority, mentorship, or friendship. Now, this may seem totally obvious to you. Of course, most of us can observe a group of 10 people and figure out the social hierarchy. You probably do it every day. You don't need to map all 35 trillion network combinations, but that's how an LLM would approach the problem, at least for now. And even this study fails to capture the real-world complexity of social interaction. Relationships are much more than just an accumulation of facts about people and where they fit in a social hierarchy. Now you might say, wait, AI models have memory features now, and they remember what I told them last week. But storing facts about a person is not the same as building a mental model of them. You don't maintain a relationship with someone by remembering every single fact about them and the transcripts of all your past conversations. Relationships are shared histories of successful grounding. Over time, friends develop conversational shorthand, inside jokes, and references, trusts, expectations, and taboos. The context of a single relationship is constantly evolving and requires continual, multimodal learning from accumulated common ground. Social learning doesn't scale easily in the sense that building a deep relationship with one person doesn't let you skip steps with others. AI can't overcome learning inefficiency with brute force and extreme scale when it comes to personal relationships. And that is why I believe people will always have a comparative advantage in social interaction. Next week, I'll be more precise about exactly why and how social skills matter for creating economic value, and how I think the human edge in learning efficiency might translate into the jobs of the future, and whether those jobs could pay decent wages. See you next time.